The angle is 1/2 the arc, or twice the arc, sorry. The arc is 2 of these. Okay, we all understand, we took the quiz or the test over it last class. That's wonderful. Now, let's look at a different angle. Angle RAT. So, RAT. Maddie, where is the vertex of that angle? Okay, so Samantha, what is that? How can we, what type of angle is that, using our circular terms? If the vertex is on the circle.
If it's on the circle?
Just like this one.
Right.
Okay, yeah. So this blue angle, angle RAT, its vertex is on the circle. So this is considered to be an inscribed angle as well. Jonathan, what is the blue angle's intercepted arc?
Minor arc AT.
Minor arc AT. Isn't this the same exact arc as the other inscribed angle? So what can we conclude about these two angles? They are congruent. If two inscribed angles intercept the same exact arc, which they are, minor arc AT, then that means those two inscribed angles are congruent. I know it looks a little funky because this one, there's like one of the sides of the angle is existing outside, but that's technically an inscribed angle because the vertex is on. So, I know that this angle here in bluing is congruent to that angle there. Now I'm just going to outline some pre-existing segments in certain colors. And I'm going to focus on some triangles. We have this large red triangle here, and then we have this smaller blue triangle there. Do these triangles have any other angles in common? What? Angle what? Grace A, please just say it loud and clear. ART. Okay, cool. I did not hear a single person say that. That's fantastic. Or I could just say angle R. Angle R. Good. And so it's congruent to itself by the reflexive property of congruence. So what can we say about these two triangles? The red one, the big one, and the blue one? They're similar by what, Theo? Angle similarity. Let's pump the brakes right here. Are we okay with what just happened? Okay. We proved that those two angles were congruent because if two inscribed angles intercept the same arc, then they are congruent. That's why those are congruent. Then, when we focused on these two different triangles, we realized that they both share angle R. And so now we see that these two triangles are similar by angle similarity. They are in completely different orientations, okay? Because we have dealt with similar triangles a whole lot. And there have been some very basic problems where it was ridiculously easy to identify what the corresponding parts were. But we need to use our angles, and so I know that maybe some of you didn't think about it this way, but when you are matching up the corresponding parts, you can use the angles. So I know that this side length from this small triangle that's 2 units, I know that that has to correspond with this side because it's formed by the two angles that have 1 mark of congruency and 2 marks of congruency. So I find that side in the other triangle. 1 mark of congruency, 2 marks of congruency. That's why I know 2 goes with 4. So I write a ratio of corresponding side lengths. We set that equal to another set of corresponding sides. This side is created by 1 mark of congruency and 3. So I find that side in the other triangle, 1 and 3. So I know that x must go with 6. Then we can cross multiply and solve this. It's very difficult. It's not very difficult, but it's much difficult when it's not in the same orientation. And it's not as obvious right now which side is corresponding with which side from the red and the blue. But let's use these angles to help us out. So let's look at from the red triangle. From the red triangle, I have got this length x. And so if you only focus, just try to delete the blue triangle out. If you look at the red triangle only, that side is created by, or is in between the angle with 3 marks of congruency to the angle with nothing. That obtuse angle in the red triangle, we have no marks in that whole angle. So you're going from 3 to none. Find that side in the blue triangle and tell me what is representing its length. Y. So in blue, coming from the blue triangle, it is this length here. Because this angle has 3 marks of congruency, and then you go to this obtuse angle that we don't know anything about. So that's how I know that those two sides are corresponding. Okay, let's go back to the red triangle. We see that we have the length Z being the side that goes from the 3 marks of congruency to the 2. Find that corresponding side in the blue triangle. What is representing its length? X. So focusing on the blue triangle, this is the angle with 3 marks of congruency, and we're going to the angle that has 2 marks of congruency. So this side is corresponding with that one. So this is a true proportion because we know these triangles are similar. Now we can do what we've always done and take the cross product. I've got x times x equals y times z. This is a true statement because those sides are proportional. So what we see is, I told you that we need to focus on the portion that's on the outside. We're going to compare that to the whole length. But sometimes when you have tangents, the outside is the whole. But we're still going to be in that mindset of outside and whole. So what's going to happen is, you can set equal the outside, we'll use this one, the outside length times the whole length. You can set that equal to the same thing of your other secant, your secant segment or tangent segment. The outside, x, times the whole, and in this case, since it's a tangent, the whole is x. So this is our theorem in our notes, that we are able to, because if we add in auxiliary segments and we prove that angles are congruent because they're both inscribed at the same intercept arc, and because if we notice that reflexive property of congruence, and then they're similar by angle-angle similarity, and then we set up a proportion, yada, yada, yada. Someone did this over and over and over and over again, and finally we're just like, man, this is nonsense. There's a pattern. Let's make our lives easier. Let's set up a theorem so that we don't have to do this every single time. This is why it works, but we are allowed to take the outside length and multiply to the whole length. And set that equal to the same thing for our other either secant segment or tangent segment. Outside times whole will equal outside times whole. So going back to our notes, I want you to write the product, plural, products that you're going to set equal to each other for number 3. For number 3. Let's hold off on solving it. And I wanted to make sure that everyone is aware that you do have this printed out. Like this whole theorem and how it works. Here is an example where you have 2 secant segments. And I want to make sure that everyone understands is you're taking the length of the outside, A, and you're multiplying that to A plus B. That is this product there on the left. And then you're going to set that equal to outside times whole. Please notice the use of parentheses. Parentheses are your friends. And you will see in a minute how much easier, if you use parentheses, it'll make your life. And so we have A times this quantity that I put in parentheses. If it is a binomial, that prefix bi means 2, like a bicycle has 2 tires. Bifocals, because there's 2 different, not settings, but you know what I mean, for far-sighted and nearsighted bifocals. Who created that, by the way? Nice, Benjamin Franklin. Why? Was he nearsighted or was he farsighted? He was both. That's why he created it. Anyways, fun fact for you. So, whenever you have a binomial, that's 2 terms being added together that you cannot combine, like unlike terms like x plus 2, please put those in its own set of parentheses. It'll help you out so much. It'll help you out so much. And then here's an example of what we just got done with. So we have outside times the whole is also a. What's a times a? How can I simplify that? A squared. Okay, so that's why it has a squared over here on the formula. Then it's set that equal to same thing, outside, which is b times the whole. What scenario is missing? I've got two secant segments, and then I got one secant segment and one tangent segment. What scenario is missing? Two tangents. What happens if you've got two tangents? I'm not asking you to draw this diagram, but let's just think about this.
Square times square. Or square so it'd be like x squared equals y squared.
Okay, sweet. So we're applying this theorem. We're applying this that we have outside times whole, x squared, will equal outside times whole. Now I have this equation where x squared equals y squared. How can I simplify that? Say it louder, Maddie. Take the square root of both sides. Whatever you do to one side, you have to do to the other. So if I take the square root and the square root, then I'm going to get x equals y. We've already talked about this. If you have two tangents from a common exterior point, then those two tangents are congruent. So even if you forgot that theorem, you can still apply this whole outside times whole equals outside times whole. Okay? But that's why I didn't include that situation down here, because we've already discussed it. If you have two tangents with a common exterior point, they will be congruent. Their lengths will be the same. That was on the test that you took last class. Sweet, okay. What are the products that you're going to be taking for number 3? First, let's deal with that tangent segment. Tangent segment. What two values am I going to be multiplying for this tangent? And then it's a segment, because there's a clear beginning and a clear end. You probably would be writing it underneath here, but I'm going to put them down. Yes, ma'am?
24 times 24.
24 times 24. If you simplified it and wrote 24 squared, fantastic. Good job. Equals. So I got outside times whole. For a tangent segment, the outside is the whole. And then what about this guy? I've got this secant tangent, or secant segment. What two values am I going to be multiplying one another? This man, Scarlett.
12 times 12 plus x.
12 times the quantity 12 plus x. And again, I've already discussed this, but if you put 12 times x plus 12, you're fine. Okay? But notice that I put this, my binomial, 12 plus x, the length of the whole thing, I put it in its own parentheses because now we can clearly see that what do we got to do with this 12? We have to distribute to both the 12 and the x. So please, this is basic algebra. Don't let your algebra skills get in the way of your geometry knowledge. I think that's a lot of us right now are feeling defeated by geometry, but that's not the case. This stuff's easy. Outside times whole equals outside times whole. It's multiplying radicals, it's quadratics, it's factoring, it's stuff from algebra 1 that's killing us. Okay, what is 24 squared? 576, and then we're going to get, when we distribute that 12 correctly, emphasis on correctly, 144 plus 12x. So I don't want the exact answer, but Taylor, walk me through. What am I going to do next? Okay. We're going to subtract 144 from both sides, and once we get that, then what's my last step that I'm going to complete or do? Wonderful. All right, and those of you who have already done it, if you follow Taylor's instructions, what are we going to get for x? 36. So x is 36, meaning the length of the whole secant segment would be 48. Let's do the same thing for number 2, but let's not get too ahead of ourselves. Let's first just set it up. On number 2, just to the left of that one, on your notes, let's set it up. Write down the two values that you are going to take the product of on either side of the equation.